about garbage collection, can't speak, and GCs in the JVM. So if you want to share your screen, we'll sync you up and get you started and not waste any time.
Sounds good to me. So hopefully you can see my screen.
You can see your screen and it's over to you.
Excellent. Thanks a lot, Mark. So hi, everyone. My name's Alex Blewitt. For those of you who don't know me, I've been hanging around in Java for quite a long time, picked it up when it first came out in the 1.0 release. And then on and off over the years, I've been using Java for a variety of different things in a variety of different companies. Most recently, I write for InfoQ, and you'll see some of my Java posts there. But for my commercial life, I work at Santander, who've generously let me do this on my own personal behalf. So this is going to be a talk about the garbage collectors in the JVM and the different ways that they work. It's going to be aimed at a sort of an introductory level. So you may know some of this stuff already, but I have put some links at the end and I've uploaded this presentation so that you'll be able to see it later on as well. So what is garbage collection in the JVM? Well, the JVM has automatic memory management, which means that when you create and run programs, it will generate the objects in the garbage collected heap. And then you worry about freedom because when they go away, they no longer get referenced and the JVM cleans them. Most garbage collected programming languages depend on something called the generational hypothesis, which is when you have an object that's created quite soon, then it will either die very soon or it will die quite some time into the future. And so quite a lot of garbage collectors have a generational phase in them where they split the processing in a young and an old region. When objects get created, they get created in the young region. If they outlive that, then they get promoted to an old region. And in fact, in the JVM, the young region and the old region can be cleaned with different garbage collectors. So objects initially get created inside something called the Eden space. So the Eden space, or the nursery, is where the object will first be created. And although logically it is a block of memory, in fact, the way that it gets split up is into something called thread local allocation buffers, or TLABs. And the TLAB is then specific to a particular thread that's doing allocating. So the first time a thread creates an object in this particular garbage cycle, it will acquire a new TLAB if it doesn't have one, and then update objects in there simply by bumping a pointer in. And other threads that get created will also have these as well. Now, as a thread allocates, it will fill up a TLAB until it gets to the end, in which case it will then request a new TLAB to fill things up. The reason why we have this is because it makes allocation very fast. You can allocate gigabytes per second on a JVM because each thread individually is just bumping a pointer to append new objects into the current TLAB that it has. And because different threads are working in different parts of the Eden space, they have their own bump pointers. And it's only when you allocate something new inside, when you allocate a new TLAB, that you need to do any synchronization options. But you can have allocations that happen outside the TLAB in a couple of different places. One of them is when you want to create an object that's too large to fit in the current TLAB, but if you just requested a new TLAB, you'd waste a bunch of space, in which case it effectively becomes its own separate TLAB, its own object within the Eden space. And another type of allocation that will live outside of the TLAB is when you have an object that's too large to fit in the Eden space. And different garbage collectors have different ideas of what means too large, but sometimes those objects are allocated directly into the old space to avoid the initial young cleaning operation. Because these allocations outside the TLAB are infrequent, some profiling tools use these to monitor how much your objects are being created in the VM, and then statistically can give you an idea of where your hotspots are in an allocation process. When the TLAB is finished, the waste space inside there and the waste space inside Eden is filled in with a dummy object, which is actually just a variable sized array. And this makes parsing heaps easier when you do a heap dump and for the garbage collector to step through. So allocations happen inside the Eden space, but when the Eden space is full, they need to be cleaned up. Now, the goal of a minor GC is to take everything inside the Eden space, decide if it's dead or alive, and then move all of the alive ones into a survivor space so that the Eden can be completely reset and start again afresh from new. In fact, the survivor space is split into two different parts, the to space and the from space. And these are logically different areas in memory, which one is the from and which one is the to kind of alternates between every other garbage collection, but logically there is a to space that you're moving objects into and a from space which you're pulling objects from. And the Eden is a space that you're pulling objects from, and the prior survivor space is an object that you're pulling survivors from as well. What happens at the end of that is that the from space is completely empty or filled with dead objects. The Eden space is empty or filled with dead objects, and so both of those can be recycled afresh. Now, what happens is sometimes when you move objects into the to space becomes full. And so there's a first in, last out type operation that goes on where it bumps objects from the to space into the old generation when they overflow. And which one flows out depends on how old the objects are. So each object has got an age associated with it, which is essentially the number of garbage collection cycles that has survived so far. And in fact, when you process the to space, if it goes above a certain threshold, which it defaults to 15, then it will automatically move those objects from the survivor space into the old generation. Now, this threshold can be fixed at startup, or you can customize it, but quite a lot of garbage collector algorithms in the JVM will actually learn what the threshold should be. So if you're generating lots and lots of objects, which typically happens during startup, you might have a lower tenuring threshold for being able to move objects into the old generation. But as the program runs, you may have a variable amount of objects being created, or even no objects in a steady state, in which case the tenuring threshold will be reset afterwards. When you look at a heap dump, you can actually get an idea of which classes or which instances of classes have particular age bands. So if they have ages 1 or 2, then they've only survived a couple of collections before dying off. You know, those are transient objects that you're being created, things like maybe JavaNet URLs that you create and then dispose of on the fly. If you have a lot of objects with a high number of tenures, then those are the ones that have outlasted the JVM, your garbage collection program, and they will be the old objects or the mature objects that you have in your application. But when you see an object where it has a variety of different ages inside there, it could indicate something like a memory leak, because you're always creating new instances of these objects. Those objects are always going into the old space. And so that's something that you can look into. Now, the algorithms that are used to process the garbage collectors actually vary depending on whether you're talking about the old generation or the young generation. And so for the young generation, you can have serial, parallel new, or parallel scavenge as options. And for the old generation, you can have serial, parallel old, or concurrent mark sweep. And you can actually turn these on and off. One of the problems with the JVM is that it has actually got quite a lot of potential combinations, and there are other ones that aren't listed here. And so over the last few JDK releases, some of these less popular combinations have been taken out. And in fact, concurrent mark sweep is something that is going to be deprecated and removed in the future as well. So we'll just have the parallel and serial options for the young and for old. However, there are a bunch of new garbage collection algorithms which deal with the heap holistically. So things like G1, Shenandoah, and ZGC have a different approach to being able to manage the heap, and they don't specifically have generations like young and old inside there. Now, how does the JVM decide to pause to do its cleanup operations? Well, let's say you have a multi-threaded application and all of these threads are running on. When the JVM decides that it's time to do a garbage collection, it will try and bring everything to a halt with something called a safe point trigger. And depending on the version of the JVM that you're using or which flavor, then there may be different options for doing this. Hotspot will simply set a region of memory to be non-readable, and periodically within the JVM's execution, either every couple of bytecodes or at the end of counted loops, it will check to see if it can read from this location. And as soon as it can no longer read from this location, that indicates that there's been a safe point trigger and the threads are brought to a stop. But there can be some time between when the JVM decides that it wants to trigger a safe point and the safe point actually having been reached with all of the application threads that are being run inside there. Once we're at a safe point, the JVM can then do whatever cleaning it needs to do, for example, running garbage collection threads, and then we end up at the end of that with the safe point end, and application threads can continue running after that fact. So the time where the GC threads are running is actually the time where your garbage collection algorithm is actually doing work, but the application stop time is the time between when the JVM wanted to go into a safe point and when it actually finished doing all of the work that it needed to. And so there's something called the time to safe point, which is the gap between when the JVM decided to trigger a safe point and when it could actually start doing some work in there. If you have applications that are taking large amounts of time in garbage collection, have a look at the logs if you do print application stop time in older versions of the JVM, or if you look in the log GC debug flags, you'll find out the application stop time. But that will be the actual time that it's taken out of your program's running time in order to be able to do processing. Typically, you'll find long times to save points are either going to be things like you've triggered loading in some unpaged memory and the OS is doing some work behind the covers, or you are doing some sort of processing in a large counted loop, and that large counted loop, because the JVM thinks it's going to terminate eventually, will wait until the entire loop finishes before it brings it to a save point. Now, there's different combinations that you can have. This is called a parallel garbage collector, where at the garbage collection time, you have multiple threads being able to run. There is the serial garbage collector, which only has a single thread for doing garbage collection, but garbage collectors can also be concurrent. And concurrent means that it has garbage collection threads running at the same time as your application. And so it's possible to have, for example, a concurrent parallel garbage collector. Why is this important? Well, depending on what you're trying to optimize for in your application, you may decide to choose one or other of these things. The serial garbage collector, for example, is good on low heap and also on very low power devices, because it's about computationally the most efficient one that you can run. But if you've got spare energy and spare cores available, then having a concurrent and parallel garbage collector is definitely the fastest way of being able to get through the work. We talk about in the JVM space about having a throughput collector. A throughput collector is really the generalized name of garbage collection algorithms which operate as efficiently as possible in terms of getting through large amounts of data, but don't necessarily have the best quality pause times inside there. So how do we do the garbage collection? Well, we go through what are called the root sets. And the root sets are essentially things that are derived from thread-based roots, so things like local variables, method parameters, any objects that you've created in the process of executing that method, and other parts of the JVM, so things like intern strings or possibly handles that you've created from JNI references. These are essentially starting points of the graph to find out all of the live objects. So any object that's in a thread is assumed to be live on the stack, and it will then chase those references down to find everything that that points to. And so, for example, if you have something like a class person object that you've created inside there, then that person will point to the class, that class will point to the class loader, that class loader will then have other references inside it. And the classes are where you store static variables, and so they're followed as well. So traversing the whole JVM essentially is a set of identified starting points and then iterating through and following all of the references from there. Most collectors that you have will have some form of being able to split apart the heap in a particular way. We've talked about the young and old direction, but you can also have regional collectors. And regional collectors split the memory into different regions or pages depending on which garbage collector that you're talking about. What will happen is that the JVM will decide to process a subset of those regions or pages to clean up the most amount of space appropriately. The reason why the new algorithms have started to move towards this kind of approach is that you can then control how long the pause times in the application can be. Because if you want to generate, if you want to free up more memory, then you can select a larger amount of pages. If you want to do the smallest amount of processing possible, then you can have a smaller number of regions inside there. And the regions generally have flavors that are equivalent to Eden and the two spaces that we have looked at earlier. ZGC uses a slightly different way of handling the heap space in that it uses virtual memory and tagged pointers to be able to identify what state individual objects are in. But for a lot of these, the garbage collecting algorithm has moved from being a lot of work done in the pause time to being more and more work being done concurrently whilst your application is running, and in some cases co-opting the application threads to be able to do fix-ups on the fly. So the garbage first collector, or G1, is one that was designed to try and collect as much garbage as it can. So it identifies in the regions that you've got kind of like a rough percentage of how much that region is used and where you're going to be able to pull content from. And what it will do is it will collect, so-called Eden and Survivor regions and potentially some subset of old regions, and then sweep them into one or more new two spaces that it's creating, or old regions for its processing. It does do concurrent marking for the application. So once you've identified the root set, and in general, identifying the root set is a stop the world operation for all garbage collectors, it will then chase those references concurrently and whilst your application is continuing to run, and it assumes that as you are running, any objects that you have created since the start of the GC cycle are implicitly live. So it will concurrently mark all of the objects, but garbage first will then have an evacuation or relocation phase, and that has to run in G1 in a stop the world phase. So the garbage first JVM memory layout is split up into a number of different regions. Each of those regions you can think of as being either the Eden or the survivor or the old from before. It also has what are called humongous regions, which are essentially objects that are too large to fit in one single one. So a humongous region only has one object inside there, typically large arrays, for example. And what will happen is it will sweep through the Eden spaces, collect them into different survivor spaces, and then create a new Eden space for next time. By doing this and focusing on the most recently created garbage first, it can do the minimum amount of work possible, but it does have a stop the world phase for doing this relocation. Shenandoah is another new algorithm that's sponsored by Red Hat and has been available in the JVM since Java 11. And this works in a similar manner, except that it does concurrent evacuations. And the concurrent evacuations work by having what are called forward pointers. It used to be the case that Shenandoah had an implementation specific for the forward pointers to then say that when you want to look in this object, you have to go somewhere else, but that forward pointer was stored in a separate word. That has been fixed in the recent versions of Shenandoah, and whilst it still stores the pointer, it reuses part of the existing object space to store that forward pointer in. So it doesn't take up any additional memory from, for example, what G1 will do. Shenandoah employs what are called load barriers, and those load barriers are when you want to pull up a reference, it will check to see whether the object that you're looking at is actually one that has been relocated on the fly, but it has fast paths so that if there are no forwarding going on, it's just a simple mask for the object itself. Shenandoah also works on 64-bit and 32-bit systems and can support compressed OOPs. And so this picture of the Shenandoah algorithm was taken from the Shenandoah page on the java.net site. And what the blue regions indicate here are effectively the Eden regions. They're the ones that have been newly allocated. What happens after a mark is that you then have an idea of what objects are live. And then the concurrent evacuation takes some subset of those regions, writes them into a new region, and then marks them up as free. So in the third block, in the one penultimate block on the left, we've got some squares which have just got yellow squares inside them. Those yellow squares essentially are objects that have been evacuated, but we are maintaining pointers to the new place so that any part of the application that's then loading up those references can fix it to point to the new location. And then once all of those evacuations are done, those areas are then free for additional use. So in this particular case, the only things that are stop the world related are the marking and update reference phases, the ones that are marked in red inside here. Everything else is done concurrently with your application, so it has a minimal stop time. ZGC is an algorithm that has been sponsored by Oracle. That's been around since Java 11 as well. But it has a similar sort of idea, but rather than having separate spaces to be able to evacuate objects into, it uses what are called colored or tagged pointers. And those tagged pointers are essentially multiple mappings of the virtual memory space to the single heap. And then when you load an object, again, it uses a load barrier like Shenandoah does to figure out if it's looking at the right copy of the object through the virtual memory space. It does use a lot more virtual memory. It doesn't use much more physical memory. And like with Shenandoah, it can concurrently fix up references that it looks at the wrong place, that looks at the different place. One difference between Shenandoah and ZGC is that ZGC will require 64-bit virtual memory to operate, so it doesn't run on 32-bit systems. So this is an example of what ZGC actually looks like. We've got one heap memory, which is the green box on the right with an object inside there. That is then mapped multiple times. They're called map 0, map 1, and remapped, I think. And what happens is if you've got an object that's pointing to an object in the wrong flavor of the heap, then when the object is moved, the object reference can be updated to point to the right version. And that can be done either by the garbage collector or by application threads being co-opted to do part of the application work. And one of the differences with ZGC is because it uses multiple threads to do processing inside here, it can actually process multiple regions or pages in ZGC terminology at a time. So each thread will work with a set of regions that it is responsible for cleaning, and there may be some additional advantages from a NUMA perspective by doing so. So if we have a look at how the different collectors fit together, there are different regions that are involved with the Garbage First, Shenandoah, and ZGC. Not all of them are generation, although they do have some slight flavors of generation. The ZGC is planning to add some generation support specifically for Eden and later spaces as a means of being able to get further processing. But the key benefit of either Shenandoah or ZGC is that they do concurrent evacuation. And that evacuation is a stop the world phase in G1 and is the biggest contributor to G1 pauses. The other difference that's worth pulling out of this is that ZGC doesn't work on 32-bit platforms. So Shenandoah can still be used on Java 11 and Java 8 with backports, but they have the different they have the support for being able to run on 32-bit, and therefore, because they can run 32-bit or 64-bit, they also have the support for compressed oops, which ZGC doesn't do. Mostly speaking, Shenandoah and ZGC are equivalent in terms of how much memory you can throw at them. 8 megabytes is a reasonable minimal limit for both of those ones. ZGC has a maximum upper limit of 16 terabytes. Shenandoah, I suspect, will handle 16 terabytes, but given that I don't have a 16 terabyte machine to test on, I've not been able to prove that for myself. But the maximum pause times for both Shenandoah and ZGC are in the order of milliseconds, whereas G1 can be in the order of seconds, depending on what you're doing. And lastly, Shenandoah and ZGC need to have unlock experimental VM options at the moment, but they plan in JDK 15 to move to non-experimental status. So in JDK 15 and above, you won't need to use that flag. However, Alexi pointed out to me that the Red Hat builds of 8U and 11U don't require you to specify the unlock experimental VM options, because Red Hat considers both 8U and 11U with Shenandoah to be production ready. So Java garbage collectors have evolved forwards to deal with both larger amounts of memory and lower pauses for stop the world time. And by taking advantage of more threads and more cores, they'll be able to do things more concurrently and therefore be able to have tighter response times for when you need to do it. The pauses now are limited by the root set, so the number of threads, the size of stacks, the objects that you create on the threads themselves, rather than the amount of heap space inside there. And most operations are performed concurrently in these regional GCs, although in G1, both the young and the evacuation phases in the old region are still stop the world, which is why G1, although performant, doesn't have the same low pause times that either Shenandoah or ZGC have. And there are edge cases that continue towards more and more concurrent operations. And although there are still some stop the world pauses, they are getting smaller. And what we're seeing now as both Shenandoah and ZGC become productionized is that they're tidying up some of the loose ends, like concurrent class unloading, for example, in their implementation details. Thank you very much for listening. I'll put some links down at the bottom here, and I've uploaded the slide deck to Speaker Deck if you want to have a look on there. And now happy to take any questions.
Thanks, Alex. Thanks very much. So I've got a question for you. How does analytics tooling support the different GCs?
So by analytics tooling, you mean in a heap dump mechanism or in terms of listening to the GC events?
Why don't we go through both?
Okay, so as far as the heap dumps are concerned, the heap dump information you're going to get is going to be pretty much identical between both of them, because a heap dump is a snapshot in time of what your heap actually looked like in terms of the object references between them, rather than specifically anything about how those object references are laid out. As far as the profiling and monitoring tools go, there is a unified GC logging in newer versions of the JDK, and so all of the GC operations now use that same unified logging format, which makes it slightly easier for being able to understand what they are. There are some different terminologies between things like minor GCs, major GCs, mixed GCs, and so on, that maybe tooling needs to be able to pick up on. But the way that those memory spaces are represented to the user are still shown via, for example, the JMX memory pools. So when you're running a VM with G1, you can ask it what the memory pools are, and it'll tell you you've got an Eden and an old and a survivor to and from, and you can monitor the weights of turnaround for both of those things. Don't think in ZGC it will particularly expose the different levels of mapping inside there, but all of them will have ability to find out, for example, what happens in TLAB rollover, and if you're just looking at them for monitoring how many objects are being created, then they'll all hook into the same part of the process that's using TLABs, and therefore we'll be able to tell you how and when those TLABs roll over.
Great stuff. And also, how do new GC type models, how can they be used in Java 8 apart from Z, is a question from Naveen R. How can you use these things in a Java 8 VM? Was that the question? I believe so, yeah.
So G1 GC is available in Java 8. It's not the default. It became the default in Java 9, but in Java 8, if you wanted to use G1, then all you need to do is start the VM with -XX plus use G1 GC. If you want to use Shenandoah in Java 8, then you can download the Red Hat Java 8 builds, because they will have Shenandoah support enabled in them. And in that case, you can just use the use Shenandoah GC for that runtime. If you are using a build for Java 11, then from, say, Adopt OpenJDK, then you might need to have the unlock experimental VM options to be able to use the Shenandoah. But Red Hat specifically are backporting Shenandoah into the Java 8 and Java 11 runtimes. I'm not sure whether anyone other than Red Hat provides builds for Java 8 with Shenandoah support enabled, but certainly Red Hat do.
Great stuff. Alex, thanks very much for joining us today. And please stay safe, stay home, stay healthy. Everybody, we're going to be taking a break fairly soon. Remember that this is, it's all been organised today for a worthy cause as well, and we are raising money for charities. Also, so if you want to help out on the effort there, head on over to ordertalks.org/tickets, and you can find out more information on how to do that. We're going to take a break now, and we'll see you again in about 30 minutes. Please go and grab some beverages or refreshments. Take care.